So today, let's see an example from the cutting edge of wireless research to demonstrate the challenges of designing and testing trustworthy embedded AI solutions. So please welcome Dr. Kaushik Chowdhury from Northeastern University and Dr. Amar Haj Omar, NI's internal expert on this topic, to discuss more on this. Welcome, guys. Welcome, Dr. Chowdhury. Welcome, Amar.
Greetings, everyone, and give thanks, Professor Kaushik, for being here.
Amar.
Could you tell us about your research in Northeastern University?
Sure, Amar. I work at Northeastern University, where I research the use of machine learning to design wireless applications that will have good performance and reliability. I started on this journey about 5 years ago as part of a seminal DARPA program which required me to find a unique fingerprint of an emitter. And you can imagine there are network security implications there. More recently, as part of the only wireless-focused AI institute funded by the National Science Foundation, I'm researching ways to do data fusion that combines data from a multitude of different sources, like LiDAR point clouds and camera images, to speed up wireless decisions.
Very impressive. Can you walk us through some examples that illustrate the value of embedding AI?
Sure, Amar. So first, to safely navigate our roads, autonomous cars must have a highly reliable network connection to a roadside base station. But how would you do this in a complex environment like a city with network congestion, with those reflections from the tall buildings downtowns? So to enable and to solve these problems, we have created digital twins, that is, digital replicas of the real world, complete with high fidelity. And models trained on these virtual digital twins can speed up wireless decisions in real time, allow the system to make sub-millisecond level decisions that greatly improves the responsiveness and the reliability of these vehicles in the field. In fact, this has created about an 85% improvement in the performance of the vehicle to find the best possible signal in these network conditions. As a second example, assume that there has been an emergency event and first responders must now coordinate effectively and communicate for a response down to a dispatcher. This means that they must have a very highly reliable network connection. Now, as you can see in the video behind me, initially there is no problem, and the first responders can communicate to the dispatcher. The frame error rate is low. But then an interferer pops up, and because of this, the network is saturated. The first responders are unable to communicate, and the frame error rate shoots up. Now, we've been studying how self-organizing drones powered by these advanced AI/ML methods running on NI USERPs mounted on the drones can cooperate and form a distributed beamforming array. Together, they can restore the signal strength and drive the frame error rate down. In this case, we have shown that this AI models can achieve up to about 40% improvement in the quality of service and about a 50% improvement in the network performance over more traditional approaches.
The possibilities of embedding AI into systems like these are mind-blowing and seemingly endless, but so are the numbers of variables these systems must deal with in the real world. Kaushik, with trust in AI being a huge topic of conversation, what are the key elements to building a trustworthy AI system?
Amar, you're absolutely correct. With great power comes great responsibility. And it is the responsibility of every network engineer and scientist working with AI/ML methods to ensure its safe and trusted use. In fact, from my own experience, there are two very important considerations that you would like to see in this deploying of these systems in a trustworthy manner in the world. First, in AI-based systems, your training data is your algorithm and IP. Unlike a traditional system where you would directly code the behavior you want, in an AI/ML-based model, you would provide it a data set with thousands or millions of these data points, and each such point will give an instance of the input and what the system is likely to do in the real world. So you can imagine that having high-quality training and validating data And then the systems and the tools to manage this data is of crucial importance. And you have to do this before you can trust the system will work in the real world with its infinite possibilities.
This is a really important point. If you want to train an AI to recognize an image of a cat, you can find plenty of data in the internet. But until recently, data needed to train wireless network has not been available. So we partnered with Professor Kaushik, and under the funding of the National Science Foundation, we released an open source code that enables engineers to collect and manage wireless data set. And it's called the RF Data Factory, and it's available on GitHub.
In fact, systems level test is the second most important consideration to ensure that products that are deployed in the real world are deemed to be trustworthy.
And this is the real challenge. Today, most test equipment is based on a model where we have a data sheet that tells us exactly how a product should behave when subjected to a series of tests. But there is no data sheet for an intelligent trained algorithm that must exist in the infinite possibilities of the real world.
So to test such products, we need a shift to a scenario-based testing methodology where we would simulate the world with all its complexity. So in that example, we would simulate the interaction between the drones, the reflections of the buildings, the spectrum congestion, and we can all imagine and understand and appreciate the importance of thorough virtual testing before anything gets deployed in the real world. And even once purely virtual AI testing is complete, the next step is to test the AI-based system with real physical inputs. Now, in a lab, our test and measurement equipment must generate a series of highly synchronized and time-varying inputs and outputs resembling exactly what the real physical system, the real sensors in the system are likely going to see in the real world. And that is a hard problem.
And some might say that's a DARPA hard problem. Years ago, at an NI Week keynote, we featured a system called the DARPA Coliseum, which is a parallel channel emulator. The Coliseum is one of a kind that combines hundreds of NI software-defined radios with massive real-time processing. Once the DARPA challenge concluded, it was entrusted to Northeastern.
That's right, Amr, and I believe we are very fortunate to have a resource like the Coliseum at Northeastern. In fact, that drone experiment that I showed you earlier required us to emulate the system in the Coliseum and gather valid training data to refine it and test it under very good emulated conditions. But there's one problem. There's only one Coliseum in the world.
Which is why we started here at NI to scale these capabilities to every engineer. In the demo on the screen, we've produced and enhanced the capabilities of the Coliseum, but within a single PXI chassis with processors and FPGAs. Basically, the Coliseum in a box. In this demo, we have two wireless transceivers communicating with the real-world environment, Austin Airport Traffic Control Radar Tower. To emulate our device under test, we've built a very simple AI-based system which detects degradation performance. It learns to frequency hop. The degradation is due to the high power levels of the radar. As Professor Kaushik said, when it comes to testing, the first element is to do as much as you can in a purely virtual world. And on the left, you can see us doing just that in a software simulation tool. But the final and the real challenge is to be able to test your prototype and emulate it in that environment. So on the right, you'll see that we've emulated the physical environment on the PXI chassis, where you're able to connect your device under test, inputs and outputs, tricking the device to be able to believe it's working on the real world, but in the convenience of your own lab.
Amr, while I know this technology is still in its infancy, I think NI's ability to do this kind of methodical testing at a desktop will revolutionize the way the systems are designed and then deployed in the real world.
Thank you, Dr. Kaushik and Dr. Omar. Now,